some point in time, of course, properties come along. The general notation, so that was 11, 12. The general notation is this. From I equals 1 through n from AI, which is, can be any term. It doesn't have, this is a specific example in which all terms are squared and then added up, we're adding them up. This is just an example. And we're going to come to that, back to that, because this is an important sum that we have to remember. But what does this mean? It really means A1 plus A2 plus dot, 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 exactly 3 dots, AN. So there are several properties which we will be using of the sigma notation. Very easy to understand, very easy to remember. So let's say we have the sum of two general terms. So these are this is the general term. From I equals 1 through n. What do you think this equals to? Common sense. It's exactly like with the limit. The limit of AI plus BI. Same thing. It's the limit of AI plus the limit of BI. Same idea. So this is the sum of AI from I equals 1 through n plus the sum from I equals 1 through n, of course, from the other generic term. What if I have minus here? What do you think the formula will give, or the property will be? Of course, with minus. Here's the next one. What about the sum from I equals 1 through n from a constant times the general term? What do you think this will equal to? Exactly what we had before. With derivatives and with limits, what will happen? Of course, c goes outside as a constant because it's a factor from I equals 1 through n from AI. These are the properties that we will use in this section and the next few sections. So these are the properties of the sigma notation. The sum of two generic terms, the sum of two generic terms, or the difference splits into the sums of individual ones, and the sum of a constant times the general term the constant goes in front. Coming back to our area. One more time. This is our area. This was the function. The function was x squared, and we wanted between 0 and 2. So we wrote this. We wrote that the area, let's say with the left 4, was 0.5, and in parentheses, we wrote f of 0 plus f of 0.5 plus f of 1 plus f of 1.1. 1.5, of course. Is there a way of writing this in a different way? Yes. The sum from I equals 1 to how many subintervals? Exactly 4. From this 0.5 times f of xi. Because when I is 1, we get 0. When I is 2, we get 0.5. When I is 3, we get 1. And when I is 4, we get 1.5. Okay. How do we denote this? And you're going to remember something that we used before a lot, delta x. And that is, if the interval is a comma b, delta x will be b minus a divided by n. So n is the number of subintervals. In our example, we had 0, 2. Can anyone identify delta x in our situation? Let's just write, don't calculate it. I just want to write it so everyone sees it. 2 minus 0 over, which is, what was our n? 4. That's why we get 2/4 or 1/2, which is 0.5. Okay, our next step. This time I don't want approximation. I want to write the area is. This was an approximation of the area. All the previous ones, everything we've done, this is an approximation. We used 4 subintervals, and we determined this, we determined this, and we determined this. They were all approximations. But this time, I want to find the exact area. So what will I have to write in here for the exact area? I will have to write the limit as the number of subintervals goes to what? Infinity, very good. So I will have to write limit as n approaches infinity of what? Of a sum of areas. The sum from the first subinterval till the last one. And now we have to identify of what? What is this? One more time, what is this? Delta x. And multiplied by, what is this? F of xi. One more time, what does this represent? Area of each subinterval. The area of each subintervals, but we have to add them. We have to add the areas of each subinterval, of all subintervals, from 1 to the last one. If we stop here, this is not going to be the exact area. But once we add the limit as n approaches infinity, this will be absolutely exact. It will fill up everything and approaches infinity from the sum of areas. Base times height plus base times height plus base times height plus base times height for all of them. Okay, this has a name. Riemann Sum. It bears the name of the mathematician who came up with it. The Riemann Sum. So now moving forward, we are going to remember that the exact area under a graph equals the limit of the Riemann sum. Yes, like we did with the definition of the derivative, of course we have to learn the hard way first and then the easy way. So bear with me. We are not going to be able to determine the limit of the Riemann sum for anything but linear, quadratic, and cubic functions. If you say find the limit of the Riemann sum for sine x, I don't have information to do that by hand. If you say find the limit of the Riemann sum when the function is tangent, I can't. So all we can is to find the limit of the Riemann sum for linear, quadratic, and cubic functions. Any linear, any quadratic, and any cubic function, we will be able to find the limit of the Riemann sum. However, not before we learn 4 different identities. Okay, 4 identities. One plus one plus one plus dot 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 plus 1. The sum from I equals 1 through n of 1. Leave the space so we can write the answer. Okay. 1 plus 2 plus 3 plus dot 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 plus n. The sum of I from I equals 1 through n. And leave some room to write the answer. 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared is the sum from I equals 1 to n from what? Excellent. And the last, of course, 1 cubed plus 2 cubed plus 3 cubed plus dot 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 plus n cubed is the sum from I equals 1 through n from I cubed. We need to come up with 4 answers. You may remember how to prove these, or you may not. If you want me to show or prove any of these, we will. We can. Okay, so let's discover the first one. If n is 3, I'm adding 1 plus 1 plus 1. What do I get? 3. If n is 5, I'm adding 1 plus 1 plus 1 plus 1 plus 1. What do I get? If the number of ones is n, what do I get? N. That's it. That's the easiest. Okay, this one I'll give you the answer. N plus 1 divided by 2. I'll jump to the third one because it's the same thing but squared. The middle one is the most difficult to remember. N plus 1, so you have the same thing. N plus 2 divided by 6. I reversed this by mistake. I'm sorry, 2n plus 1. N plus 1 to n plus 1 over 6. Sorry about that. Okay. Let's choose a quadratic function. And let's determine, and also an interval. Choose any quadratic function, and let's choose an interval. Let's start with a simple interval with 0 comma something. So let's start at 0. If we start anywhere else, it's going to be slightly more difficult, but we can, of course, look at that. And determine the area under a graph, any function that you would like to choose a quadratic function, anything. These 4 identities are not they're not in 5.1. I don't know why. They should be here. So here it is. The sum of I, n times n plus 1 over 2. The sum of I cubed, the same thing but squared. And n plus 1 to n plus 1 divided by 6. And somewhere there must be the sum of 1s, which is n. I don't see it right here. But it has to be. I just don't see it at this moment. Okay? So let's choose a quadratic function. Okay, let's say 2x squared plus x plus 2. Is this okay? We need 3 preparations. So what are we asked to do? We're asked to find the exact area. The area using the limit of the Riemann sum. That's what we are asked to determine. Find the limit of the Riemann sum. The first example will take, like, it seems like forever. Of course, the next and the next and the next will take less. But still, they are not trivial problems at all. Because you're going to see, we're going to have to go through a lot of steps. Okay, ready? Which interval would you like to choose? Let's start with a simple interval like 0, comma. It doesn't matter what it is, but starting at 0, it will make a big difference. 0, comma, what would you like? 5 it is. Perfect. Before we even discuss and we write this, the limit of the Riemann sum, we have to go through 3 preps. First, we have to find delta x. Can anyone give us delta x? Five minus 0 over n. So this is 5 over n. Okay, number 2. We have to determine xi. What is xi? Is this number that moves from left to right. It's this number, this x value for which I determine the height. Okay, there is a long discussion about it. In our case, we chose 0 to 5. We're dividing the interval into n pieces. This is the first one, the second one, the third one, dot, 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 number I, the next one I plus 1, and so on and so forth, till x sub n. So n, or I should say, better, goes from 0 to n, as always. So this is delta x, this is delta x, this is delta x, this is delta x, delta x, delta x. Everywhere delta x. It's the base of each subinterval. Okay, so if this is 0, what is this point here? What is this x? Must be x1, which is 0 plus delta x. Can anyone give us the next one? The next x value. 0 plus delta x. So this is x2, which is 0 plus twice delta x. Okay. Can anyone give me the third one, which is x sub 3? So finally, can anyone give us xi? Very simple, right? This is 3, this is 3. If this is 1, this is 1. This is 2, this is 2. So xi must be 0 plus, of course. Very good. 0 plus I delta x. That's it. Since it's 0, I'm not going to write it, but I'm going to write I times delta x. 5I over n. We'll do this on several problems. The first one, as I said, it takes some time. Okay, next one, all I need is the last step, is f of xi. Here's f of x, and please tell me what to write for f of xi. 2 times 5I over n, everything squared, plus, very good, 5I over n, plus, that's it. But I have to simplify it as much as I can. So f of 5I over n, because that's our xi, will be 2 times 25I squared over n squared plus 5I over n plus 2, or 50I squared over n squared plus 5I over n and plus 2. When we haven't even started the limit of the Riemann sum. So let's go back for a minute. We're trying to determine the area under this graph between these 2 points, these 2 x values. So find the area using the limit of the Riemann sum. First step, I have to determine delta x. Why am I determining all these things? Here's why. I need delta x, I need f of xi, I will put the sum, and I will find the limit. So I need this piece first, I need this piece second, I need this piece third, so I can put them in the sum with a limit in front. That's what I'm doing first. These are the preps. So delta x, 5 minus 0 over n, xi, of course, 0, which is the leftmost point, plus I subintervals delta x, right? I times delta x, which was, since delta x is 5n over n and I in front is 5i over n, and then I determine f of xi, which is f of 5i over n, as 2, this squared plus this plus 2. I square first and multiply by 2, and then 5i over n plus 2. Now I'm ready. After all this work, I can put them together. The exact area of this function on 0, 5 equals the limit. As n, the number of subintervals, goes to infinity, from the sum from I equals n till the very last subinterval of what? Base. What is the base of each subinterval? 5 over n multiplied by f of xi, which is all this, and I have to put parentheses. So in parentheses, 50I squared over n squared plus 5I over n and plus 2. Is this done? Far from it. Okay, I'm going back to the properties of the summation notation for a minute. This does not depend on I. This is like a constant. I don't need it here. I'm going to put it outside of the summation notation. It does not depend on I. It never changes. Is that 0.5 that never changed outside of, okay, so it goes in front. That's our first step. Limit as n approaches infinity from 5 over n. Now, in order to save some time, look what I have the next property. I have the sum of 3 different terms. The sum, in this case, of the sum of 3 terms. This is the sum of the first plus the sum of the second plus the sum of the third. So brackets, sum from 50I squared over n squared plus the sum from 5I over n plus the sum of 2, of course, all of them from I equals 1 through n, from I equals 1 through n, from I equals 1 through n. Now, each individual piece has a constant. Can anyone give us the constant on the first summation notation that will go in front of that one? Of course, 50 over n squared. Excellent. So this is limit as n approaches infinity. 5 over n. 50 over n squared, the sum of I squared from I equals 1 through n. This I know. Plus, what is the constant that goes in front now? Excellent. The sum of I. I equals 1 through n, plus, what is the constant, and I'm helping you with this one. What is the constant that goes in front now? 2. 2, the sum of 1 from y equals 1 through n. We're getting very close. This has to be replaced, this has to be replaced, this has to be replaced. Don't cross it out like that. Of course, I'm making a point. This one is nice. n plus 1 over 2. This one is nice. How much? N. This one is not as nice. This one is n plus 1, 2n plus 1 over 6. That's my next step. I replace these summation notations. They're gone. So then limit as n approaches infinity, 5 over n. 50 over n squared times n plus 1, 2n plus 1 over 6 plus 5 over n times n plus 1 over 2 plus 2n. What did you accomplish? A lot. We got rid of the summation notations. We replaced them by something that we can handle. They may not be nice, but at least we can handle them. Okay. I will only, yes, we can simplify by 2, but I would not bother with anything else but simplifying by n, because the least common denominator is 6n. So then we have limit as n approaches infinity from 5 over n, and the least common denominator is 6n. I will distribute these two right here, right now, and get 2n squared plus 3n plus 1, because it's easier when I multiply. 6n is the least common denominator. I have to multiply 50 by these three. 100n squared, 150n plus 50, plus. The denominator here is 2n, so I need to multiply by 3. So I have 15 to be distributed to n squared and to n. So plus 15n squared plus 15n. This one has denominator 1, so I have to multiply by 6n. So plus 12n squared. Excellent. So we are even closer now. Yes, after 3 pages, I know. Okay, so then limit, and as n approaches infinity, 5. The denominator now is 6n squared. So let's see. 100 plus 15, 115n squared. 150. Oh, I'm sorry. 127. 127n squared plus 165n and plus 50. We shouldn't continue, but let's say we don't know. And we'll continue with the limit as n approaches infinity. 6n squared n squared plus 250. And we plug in. What do we get when we plug in? What is the top? Where is the top going? Good. Where is the bottom going? Okay, let's say we don't know, but we know L'Hopital's rule. So limit as n approaches infinity. Again, let's say we don't know. simplify by 2. And I think that that's it. Okay, we don't have time to, we do have like 8 minutes, so if you want to try another, but I would like to at least go through the steps one more time. And then let's choose, I like to determine and make sure that we find the area under x squared between 0 and 2, because we talked about it and we estimated it 3 times. So let's determine that, because I think we have time for that. Okay, we are given a function, we are given an interval, and we are asked to find the exact area using the limit of the Riemann sum. We are restricted. We can determine this, we can use these steps only for quadratic, linear, and cubic. Why? Because that's all we know. We don't have other formulas. We have for linear, we have for quadratic, and for cubic. There is nothing else we can determine. Good. So then, first I have to find delta x. Question is, why am I doing this? Why am I finding delta x? Because I need it here. So delta x is 5 minus 0 over n, which is 5 over n. Then I need xi. Why am I determining xi? Because I need it here. Plugged in the function. What is xi? Is the leftmost point plus I intervals times delta x, the width of each. So that's why we get 0, I times 5 over n, and we get this. We plug this in the function, and here's our function. 2 times xi squared plus xi plus 2. We squared because we had to. Over n squared. We had to multiply by 2. We got the 50i squared, 5i over n plus 2. Putting all these together, we come up with the limit of the Riemann sum. And then all we do is manipulate algebraically and apply the properties of the summation notation. We put the constant in front. We separate into 3 summations. We simplify each by taking the factor in front. And we are down to what do we know? The sum of I squared, the sum of I, and the sum of 1. We change these 3 into what they are equal to. And from here is just algebra. Finding the least common denominator, and then applying the limit using L'Hopital's rule, and distributing, applying L'Hopital's rule several times, and we got the area. So now, since we have a few minutes left, I'd like to finally determine for that function, which was x squared, on the interval 0, 2, we did not know the answer at the very beginning. We had no idea what would come up to be, but definitely it has to be a number between 1 point, what was it, 7, yes, it has to be a number between 1.75 and 3.75, definitely as close as possible to this. We don't know what it is, so let's do it. Okay, prep number 1. What do I need in prep number 1? Delta x. Not a problem, is 2 over n. Number 2 is xi. Very good, 2i over n. Number 3, f of xi. 4i squared over n squared. We agree? Good. Easy, right? Limit? Yes, after we did the first thing, it took us 20 minutes. Yep. So n approaches infinity. From the sum from I equals 1 through n, base of the interval, delta x, times the height of each interval, 4i squared divided by n squared. What goes outside in front of the summation notation? 2 times 4, which is 8, divided by, very good. But this we know, because we have a formula for that. So this is limit as n approaches infinity 8 over n cubed times the ugly one, n plus 1 to n plus 1 divided by, very good. I will simplify one n from the top with one n from the denominator. And I will simplify a 2 from here with a 2 from here. I will distribute these two. Always remember this is 2n squared plus 3n plus 1. 2n squared plus 3n plus 1. Limit as n approaches infinity from 4 distributed here, 8n squared plus 12n plus 4 divided by 3n squared. You know the answer, but let's say we don't. The numerator goes to infinity. The denominator goes to infinity. It's a nice situation. We have limit as n approaches infinity from 16n plus 12 over 6n. Again, it goes to infinity over infinity. So this is limit as n approaches infinity from divided by 6. So 16 divided by 6 is 8/3. As we knew from the very beginning, because it's the same degree over the same degree. However, what is the answer? The exact area is 8/3. And we got very close. That's what, 2.6? And we got with the midpoint, even with such a small number of subintervals, right? We got 2.6, what was it? It was 2.625. Any questions?